So hello guys, let's wait for 2-3 minutes more so that others can also join. After that, we'll start the today's session. Till then, let me make sure. Am I audible, guys? Nandan and Ghanshyam. Can you guys let me know in chat if I'm audible? Ghanshyam, if you have some question, you can type in chat. If I'm audible, can you type in chat? Okay, cool. Audible. Let's wait for 2 more minutes. We'll start at 6:05 so that some more people can join the session. Okay, cool. Some people have joined, so we'll start the session. So let me introduce myself again. So hello guys, I'm Lakshay Sargi and I'm the discrete maths TA for the Tuesday session. So this will be our second session, and in this session we'll be discussing problems related to week 3, which are the logic Boolean logic related problems. So I'll just so the flow of the today's tutorial will be today's problem session will be first we'll discuss some logic based problems, and then I believe you guys have got the solutions to your assignment 1 and assignment 2. So after discussing this week 3 problems, I'll ask you guys if you have any doubt in assignment 1 or assignment 2 solutions. Then maybe we can cover your doubts as well in this session. So I'll just share my screen and we'll start with the problem solving session for today. So just let me share my screen, guys. Okay, so I have shared my screen. Can someone let me know in chat if my screen is visible? Uh, Ghanshyam, Manish, Pratibha. Okay, okay. Nice. My screen is visible. Cool. Let's start with today's session. So today we'll be discussing problems related to logic. So I don't think these problems are very difficult. Like Boolean logic is a very straightforward topic, but nonetheless, since we are starting from the basics, so we'll cover all these problems. So like last time, I don't have my tab as of now. So I'll just be typing out the solutions in Google Docs itself. So bear with me for this, guys. So let's start with the session. So the first problem is the first problem which we'll be discussing is, so let's say that the first problem states that let P is basically a statement which says Ram likes ice cream or Sudha likes toffee. So P is basically a compound statement which says Ram likes ice cream or Sudha likes toffee. So it's, and then the question is asking what is the negation of the statement P? So like it's a very like logic questions are generally very straightforward question, but it's just testing your how to how if you whether you know how to negate a statement or not, which is quite important when you write proofs. So like when you're writing a proof by contradiction or something, you should know what is the negation of a statement. Only then you can prove the statement in a correct way. So this sort of thing is important, even though it seems very easy. So let's just start with the basics. So I'll start by typing out all the basics of this problem and then we'll arrive at the answer easily. So let's say basically the statement P is Ram likes ice cream or Sudha likes coffee, and I need to find its negation. So first of all, since P is a compound statement, let us reduce it to like two easier statements. Okay, so I can refer to so let's say statement one is statement one. Let's say statement Q. I can say let's name a statement Q, which is Ram likes ice cream. And let's say there is another statement uh, R, which okay, which says that Sudha likes toffee. So basically the statement P is sorry. So basically the statement P is nothing but uh, Q or R. Like it's easy to see because the statement P in as defined in the question is Ram likes ice cream or Sudha likes toffee. So since P is Ram likes ice cream, since Q is Ram likes ice cream or R is Sudha likes toffee, so the statement P is just Q or R. So I need to find basically negation of P. So I need to find like, let's say this symbol, the exclamation mark, I'm denoting it as negation. So I need to find negation of P. So we have so this will be basically negation of Q or R, right guys? And you must have seen in the lectures that uh, how to negate a compound statement. So it can be negated using De Morgan's law. So this is uh, equivalent to not Q. So basically in De Morgan's law, what we do is suppose we have to take a negation. So we step by step take negation of every term. So for Q, we'll take the negation and make it not Q. And for this OR term, OR will be converted to ANDs are converted to ORs, as we know in De Morgan's law. And similarly, R will be converted to not R. So this will be equivalent to not Q and not R. Correct. So it's quite straightforward, right? So not so basically, this means that uh, not P statement corresponds to not Q and not R. So another reminder, guys, like I understand that you guys might think that this is sort of redundant and you guys can do it sort of without writing it in this manner, like a stating a statement Q and R, you guys can just take a negation directly. But suppose like what I'm typing out here is a general way to find negation of a compound statement. Suppose the statement P was consisting of like hundreds or thousands of simple statements. So when you are like, suppose you need to find a proper algorithm or proper way how to convert that statement, how to find the negation of it, of that statement, then it's better to have a structured manner in which you can approach the problem, right? So this is sort of a structured manner in which you can find the negation. You just take every simple statement as a distinct statement, and to find the negation, you just take the negation and like apply De Morgan's law. So in that sense, I'm like this problem in itself is not difficult, but its solution is important because you guys will come to understand a structured way to find the negation of a statement. That's all I'm saying. Yeah. So I hope I made sense. So basically, what we did here was to find the negation of P. Negation of P can be basically by De Morgan's law. I found it to be negation Q and negation R. So I need to type it out in words now because initial problem was asking us to type it out in words. So this statement basically means negation Q was the Q statement was Ram likes ice cream. So the same negation of this statement is quite straightforward because uh, uh, yeah, well, because this is not a compound statement. So Ram likes the negation of Ram likes ice cream would be Ram does not like ice cream, right? And the negation of statement R would be negation of statement R would be so the statement R was Sudha likes toffee. So its negation would be Sudha does not like toffee. So this will be the final answer. I haven't done this answer. So yeah, so this will be the final answer. And you can see like it was quite straightforward also. Like you could have just seen it straight away that negation of this statement is this statement. But we are trying to approach these problems in a structured manner so that even if the number of statements becomes very large in the compound statement, we can still find the negation in a structured manner, in a straightforward way. So yeah. So in this manner, we can say like the negation of statement P is Ram does not like ice cream and Sudha does not like toffee. Like it's easy to see how is this intuitive because the statement P was saying that Ram likes ice cream or Sudha likes toffee. So statement P was just saying that either Ram can like ice cream or maybe like Sudha can like toffee. At least one of these statements would be true. So its negation would be both of these statements should be false. So it would be like Ram does not like ice cream and Sudha does not like toffee. So I hope I'm making sense. So yeah, this question was straightforward. So let's move on to the second question now. So the second question is like basically we are given three statements and we have to tell which of the following statements are true. So the sentence. So the first statement is basically the sentence Rajesh is a hardworking man is a statement. So if you guys can let me know in chat, what do you guys think about this statement? Is this sentence a statement or not? Like the definition of a statement, you guys must have studied in the NPTEL in the lectures also. What is basically a statement? A statement is something which is like fact based and not opinion based, right? So according to that definition of a statement, is this Rajesh is a hardworking man? Is this a statement or not? Can someone maybe type out the answer in chat so I can know at least you guys are paying attention? Okay, never mind. So just go along with it. So basically, this statement, guys, the first statement, the Rajesh is a hardworking man. So see, whenever you're calling someone hardworking is something which is more of opinion based. Someone might think like Sham might think Rajesh is a hardworking man, but Sanjeev might think Rajesh is not a hardworking man. Like hardworking in itself, the adjective is subject. This adjective is subjective, yeah, to everyone's opinion. So similarly, like Rajesh is intelligent or this is also like opinion based. Someone might think that a guy scoring very good marks in mathematics is intelligent, but someone else might think that like scoring 90 out of 100 is not intelligent. Intelligence is 95 out of 100 at least. Similarly, in hardworking, if someone studies 4 hours a day, someone might think that this is enough and this guy is hardworking. But for someone else, 4 hours a day might not qualify as a hardworking person. So the first statement is like the first sentence, like Rajesh is a hardworking man. It's not a statement essentially because of this reason, because it is opinion based, not a statement, as it is opinion based, not fact based. So opinion based, fact based, basically uh, reiterating their definitions. So basically, if you ask if you tell different persons the same thing, then the answer should not change. Like Rajesh is a hardworking man. Uh, if you tell this statement to like two different people, suppose A and B, then both A and B should agree on on this sentence. If they are not agreeing on this sentence, then it is not a statement. That's all I'm saying. Like Rajesh is a hardworking man is not a statement because A might think he is, B might think he is not. So yeah, a fact-based statement like sun rises from the east, let's say, that would be a statement. Just writing out for an example. Sun rises from the east. Like this is a statement because it is a fact-based. It's a well-known fact. Right. So no one can deny this statement, right? So just as an example, I'm covering, this is not part of this question, but yeah, sun rises from the east. This is a statement since it's a well-known. So coming to the second statement, 9 is not a prime number. So nine, basically prime numbers are the numbers which have a common, uh, don't have any factors, which don't have any divisors except the number itself and one. So basically 9 has a divisor 3. So like 9 is not a prime number. Right? It's easy to see, like it's basic high school. Not even high school, it's like basic definitions we cover in 7th or 8th. So it's a fact. Like even if you ask like even if you ask different people like A, B, or C, everyone will agree that 9 is not a prime number. So yes, stay. So the third option is cardinality of A. The third part is the third statement is cardinality of A union B is 5, where A is 1, 2, 3, and B is 2, 7, 8. So seeing, let's just see what would be like. It's a straightforward question. So just seeing what would be A union B. A union B would be here, like as we discussed in the last example. So A union B here would be like 1, 2, 3, 7, 8. Right. So cardinality of then cardinality of A union B would be, you guys can just see it is 5. So the third statement is true, right? So like this is also a statement as like it is true. Yeah, because like the definition of A union B is well defined. Like what would be the value of A union B? Similarly, cardinality is well defined. This is not subject to anyone's opinions. You can just everyone will agree that the cardinality of A union B is 5 here. So yeah. So this question was basically just so to make you guys understand what is a statement and what is not a statement. So basically, statement should not be opinion based, but should be fact based, right? So after the second question, so let me just write it out the answer. So 2 and 3 are statements. I hope I'm making sense. So let's see the third question now. So the question is basically saying if A is any statement, then which of the following is a tautology? So tautology, as we have seen in the lectures also, what is tautology? Definition of tautology is a statement which is always true. So let's say a proposition which is always true, no matter what the values of the variable, no matter the values of the boolean variables, let's say. Yeah. So basically here, like, there are four options. So uh, A, B, C, D. So first option says that A or F. Is this a tautology? So this won't be uh, option A. This won't be a tautology since its value is false if A is false. Right. So I guess this is straightforward. So similarly, you guys can just see, like, if statement A is false here, then false or false will give me false only. But tautology is something which should always give true. So similarly here, option B, let's say. So option B is saying A or not A. So here you guys can check, like, or you can just see clearly, like, a statement can be either true or false, right? If A is a statement, it will be either true or false. It can't be both, like, because it's fact-based, and a fact-based stuff is either correct or incorrect. So a statement can either be true or false. So basically, either A will be true or not A will be true. So it will be basically a tautology since. So, like, if you're just seeing, uh, yeah. So if you just want to see directly, you can just think that since a statement can be, so statement is either true or false, right? But if you guys want to see it by Boolean algebra, then you guys can just check, like, suppose A is false, false, then not A. I am denoting the exclamation as not, then not A is true. So A or not A will be, so A or not A is true. Similarly for the other case, when A is true. So yeah, so option B is a tautology. So correct answer will be option B. I'll just underline the correct answer. Still, we'll just see all the options to see why something a tautology and why something not a tautology. So option C is A and F. So will this be a tautology? Actually, it will not be a tautology. Actually, it will be opposite of tautology, because, like, in AND operation, as we have seen in Boolean algebra, so this A and F will only be true if both of these, some, like, A and B, suppose the statement A and B is true if and only if both A and B are true. Maybe I'll just denote these by some other variables, so you guys don't get confused. X and Y are true, right? But here we see that A is false here. Y is already false here. Y is false. So basically, whatever be the value of A can be true or false. It doesn't matter. Still, A and false will give me uh, false only. So that's what I'm saying. It's actually not a tautology. It's opposite of tautology. It's basically like a statement which is always false, right? And so basically, suppose I, instead of this statement, I was given a statement like this, not of A and false. Then this would be actually a tautology, since A and F, since like the reason I already wrote A and F was false. So since A and F was false, so not of this would be true always. So not of this will be a tautology. And you guys can just see it easily also using like De Morgan's law, like opening this negation over these terms. This will give me uh, not A, or basically applying De Morgan's law. So negation of A, and this and will become or, and then this F will become true. Is true. And this will be, since in or, if either of these terms are true, then the or operator returns true. So this will return true. Right? It's easy to see. So by De Morgan law also we can check that this is a tautology, and by like straightforward also, like A and F will be false and negation of this will also be true. Right? So by both the methods we see that this will not of A and F will be a tautology, but this A and F is not a tautology. It's something which is always false. So let's see option D now. So option D is something like A and true. So in Boolean logic, you guys must have like seen what this means. So A and true essentially returns the AND operator one of uh, if one of the terms is true in AND operator, then basically the AND returns the value of the second variable, right? So this will be essentially A only. So the value of this, the A and true, will depend on the value of A. So if A is false, then A and F, A and true will return false. Hence, not a tautology. It's easy to see, right? Yeah. So option B was the correct option here. So let's go to the next question. So tautology, like just again revising definition, tautology is just something which is always true. And here only option D was adhering to this definition, and all other things had a value of Boolean variable such that it could be set to false. Yeah. So now let's go to question 4. So maybe I'll just put this question in the next page. So yeah, we have more space to discuss it. Question 4 is basically saying, it is not that I don't like traveling. Suppose Rina said, it is not that I don't like traveling. So what does Rina mean by this statement, right? So let's just see this statement, like there are unnecessary negations here. So what does Rina mean by it? We'll see it step by step. So suppose we just see the first part of the statement, I don't like traveling. So this just means that Rina is saying that she doesn't like to travel. But then she says, it is not that I don't like traveling. So basically she's applying a not. So basically like uh, what Rina is saying, if you want to convert it into some sort of function, not of I don't like traveling. Is Rina is saying that it is not that I don't like traveling. So she's applying sort of double negation here. So this will basically mean it basically means that she likes traveling, right? Because like you don't like traveling, so the negation of this will be I like traveling. So, so option C is here correct. That. So basically, this is an example of a double negation. So option C, Rina likes traveling. This is the correct option. Maybe I'll just mention it here also. This is double negation. As Rina is saying that, not of, she doesn't like to travel, which essentially means that she likes to travel. She's just saying in a twisted way for whatever reason. Yeah. So option C, really nice traveling is the correct answer here. So straightforward question, I would say. So let's come to the fifth question. So yeah, here the statements. Basically, here you will need some truth tables or stuff like that for solving these sort of questions. So one thing which I would first here like to tell you guys is some notation which I would be using. Maybe you guys can also adopt this notation for like faster or easier methods of seeing the Boolean logics. So what I mean by that is, let me see. So suppose you are writing some statement like P or Q and R. So suppose like something like this, and you have to simplify this sort of thing. What does it mean or stuff like that? So I'll just so for this notation, like writing these ors and ands so many times is a little bit more time consuming, and it takes a little bit more space and essentially takes away the main crux of the arguments, right? What you want to essentially see is these variables and how are they combining, not essentially writing the notations of these odds and ands. So I'll just represent this in the form like P or Q can be represented as like P plus Q. So maybe you guys would have seen also that like or corresponds to sort of a Boolean addition, and like and corresponds to a Boolean multiplication. So for multiplication, we can just write it like this. So maybe like I'll just explain the notation. So what I mean is that for statement like mm, A or B, I'll denote it from here. I'll denote it as A plus B. So this A plus B here is not actual addition, numerical addition, since A and B are Boolean statements here. So A plus B just means like Boolean or. And similarly, I'll denote A and B as AB. Basically, the and can be represented as basically Boolean. This is basically Boolean multiplication. As you can see that if A and B both are 1, then this multiplication gives 1, else it gives 0, which is just the output of like this A and B also. Similarly, for A or B, this gives like at least 1 in case one of A or B is 1 in this addition, and this is essentially same as A or B. So I'll denote this as notation, and another notation which I was already using, but I'll just make here also not A. I'll represent it as exclamation of A. So many people represent it as a bar over A also, but I'll just like it's your preference. I like to refer to it as exclamation of A. So these notations are not necessarily you guys something which you guys also have to adopt, but I'll prefer these notations because these notations can make the a boolean complex boolean statement look in a more concise manner. Like suppose the statement was this only P or Q and this and R. This can be concisely represented as just P plus Q times R. So it just saves a little bit of time while solving out these expressions, and also gives better intuition. So maybe you guys can also try to adopt this notation, but not necessarily. But I'll be using this. So let's just see. So these are the notations mainly. And so basically the statement we have to see this statement P implies R or Q implies R is logically equivalent to. So we need to see. So like, first of all, logic, sometimes smaller statements can be just directly by your intuition or without like properly solving out these statements. You can just directly guess also what would this mean. So sometimes, so let's just look at a bit of intuition and then we'll try to like formally write it also. you guys should also know how to intuitively tell what this statement means, as it can help you solve some things faster. Right? You don't have to always go through truth tables or resolving the expression. Sometimes you can just by intuition tell what does the statement mean. So yeah. So for this, what we can do is like, let's say the statement is saying that P implies R or Q implies R. So what does this basically mean is that if P is true, then R would be true, and similarly, if Q is true, then R would be true. So by intuition, like we can just see that this will correspond to something like P or Q implies R. Like here, this statement just means that if P was true, R was true, or if Q was true, R was true. So by intuition, we can see that this would correspond to this option B, uh, because either P was true or Q was true, and this implies that. Yeah, this was by intuition, but if we want to like correct, write out, we should also know how to write out formally. Many things like break down when you are doing it by intuition. If the statements are like there is a lot of statements here. Suppose there were not just two statements, but a lot of statements. So you can't intuitively tell. You also need to resolve to some structured methods. You need to resolve them using structured methods. So let's just see here. So basically P implies R basically means uh, P implies R. We must have seen the meaning of implications. Okay, once again, guys. Yeah. P. Okay, this is okay. Maybe I'll just write it blindly. So P implies R basically means not P plus R, not P or R. This we have seen in the lectures. Basically, not of P or R. P implies R means this. So similarly, Q implies R means not Q plus R. So yeah. So basically, this statement P implies R or Q implies R basically resolves to not P plus R plus not Q plus R. Note that these are not traditional pluses; these are Boolean pluses. But still, we have seen the properties of these or that the or is in itself associative and commutative and stuff like that. So we can resolve this also. Let's just see how we can resolve this. So this can be then written as basically since or is maybe I'll just put the parentheses here also. These were the expressions, right? So OR operations are associative as well as commutative and stuff like that. So how can we resolve it here is maybe I'll just write it out as I'll leave this as not P plus R, and I'll maybe since this OR operator is like associative, I will just write it as remove the brackets and just write not P plus R plus not Q plus R, and then this can be further resolved to the order of this R and not Q can be changed. So this will resolve to not P plus not Q, not P plus not Q uh, plus R plus R, right guys? So this can further be resolved to let's put this as in this equal sign. This means that these statements, I'm just resolving these statements. This colon equals to sign. So this R plus R can then be resolved to R. So this will just reduce to, since A or A resolves to A only in Boolean logic, right? So this would be not P plus not Q plus R. It's straightforward to see. So this and this not P plus not Q can be written as this not P plus not Q can be written as by De Morgan law not of PQ, since like not A or not B is just not of A and B, right? So not of PQ plus R. And so this will just mean like if PQ is a compound statement, then this just means like not A plus B, which is equivalent to A implies B, right? So this just means PQ implies R, right, guys? So actually from this, we see that, okay, let's just so this. So what this basically means is that this statement like this P implies R or Q implies R resolved to something like this, like PQ implies R, right? I'll just put this in next statement. So this basically means like just writing out properly. This PQ implies R would just mean like P and Q implies R. Like PQ meant that P and Q, and this implication sign remains the same. PQ was just a notation for P and Q. So actually, I was wrong. The intuition which I was initially giving was wrong. Actually, the answer is option D. So this was wrong. Okay, maybe I'll just delete this. So this is also like PQ implies R. So basically P and Q implies R. So this is option D. It's implying this. So I think this makes sense, right, guys? This was basically what I did was just change the notation a little bit and then just did basic Boolean operations only. Whatever I did was basic Boolean operations and used their properties and uh, arrived to this PQ implies R statement, which is just P and Q implies R. So the option D was correct. So yeah, in this way, we can we have resolved this statement to option D. But maybe like another way, like I'm just saying that there are multiple ways to approach the same problem. Sometimes you can do it by intuition. Here, my intuition was wrong, but sometimes you can just straightforward say it by intuition, or you can resolve the statement using some properties, or also like the heaviest hammer in Boolean logic by which you can solve all the problems is using truth tables. Alternate method. So truth table is something which will resolve every logic problem, almost every Boolean algebra logic problem. But the main problem in truth tables is that truth tables are expensive to make. So here, since there are like suppose P, Q, and R three variables, so we'll need 2 to the power 3, 8 entries in the truth table. And then we'll have to check uh, basically which of these options, the truth table of which of these options corresponds to the truth table of this. So am I making sense, guys? Maybe I'll just write. Maybe I'll just write down or okay, let's just leave. I'll not make the truth table for this, but I'm just saying that using truth tables, you can also do this. But generally, this is a very time consuming method. And we prefer not to use truth tables and use other methods like using the properties and other stuff to simplify some expressions. So yeah, truth table is the heaviest hammer, but this hammer also takes a lot of time. Yeah. So just saying how to do it using truth table, and I just type out the basic method. Make the truth table for initial expression. Uh, make truth table for all options for all the four options. So here, like, you'll have to compute like this truth table will have 8 entries. One of the truth table will have 8 entries, and since there are like you have to make the truth table for the original expression and then for the 4 expressions of the options. So there will be like 5 truth tables which you'll need to make. So basically, these 5 truth tables will contain like 8 times 5, 40 times entries. So that will be a lot of work. So make truth table for all the 4 options, and the equivalent expression would be the one whose all the entries match in the truth table. So basically, since the expressions are equal, for every entry of the truth table, the expression should match. And in this way, we can use truth tables to find this. I'll not be making the truth table. It will be very time consuming. And another thing you can see is that even though truth tables are something by which you can do a lot of stuff, but generally in real life scenarios, the purpose of simplifying expressions is not for asking questions, right? So since this was an MCQ, like even for, suppose you are just given that you need to basically reduce this expression to something more simpler form. So if you are given 4 options, then you can make the truth table entries for these 4 options and then compare with the truth table of this expression. But if you're not given these 4 options, then how will you, and then what will you compare this to? Right, guys? So there won't be any truth table to compare it with. So you won't know how to simplify this expression in that setting. So yeah, so in that way, this method, like using this properties of ORs and ANDs is much more preferable. So even if we are not given these options, we can still simplify it because here I did not make use of the options. I just used the properties and I just saw that simplifying this, I was able to arrive at the option D. So yeah, just putting this information out here. So this question is done. So similarly, this is sixth question. So the sixth question is saying another expression simplifying question, not P. And this symbol is basically XOR. You guys must have seen like a XOR operation is basically when exactly one of the two entries. A in A XOR B means exactly one of A or B. Basically either or operation. Either A is true or B is true, but not both. So this can be written as this XOR is generally written as uh, A and not B, or not A and B. Like, it's easy to see how do we do it. So in our notation, how I was writing out writing ands as multiplication and odds as pluses. So this will just be A times not B plus not A times B. This is basically XOR operation, right? So just let's just try to simplify this expression. So again, we can just make truth tables for all the options and for all this and then compare the values, but that would be useless or let's say not very beneficial for our understanding. It's just a very mechanical based method. So we'll try to resolve it by ourselves instead of relying on truth tables. So not P XOR Q. So A XOR B, I have written what does this mean? Like A times not B plus not A times B. So here A is replaced by not P and B is replaced by Q. So just simplifying this expression, what I'll get is that not P, I have put not P in place of A times Q, not P times the A, it was A times not B. It was A times not B. So here A was not P and B was Q. So the first term will be not of A times not of Q. Am I making sense, guys? Can you let me know in chat if it is clear to you what I'm writing right now? Okay, cool. So similarly, the second term of this XOR will be like not A times B. So not of P would be like not of P would be P itself. So it would be P and then times B. B we set as Q. So it would be PQ. So basically not of P XOR Q is just basically not of P times not of Q plus PQ. And then we have another OR operation. This arrow is basically represents. You guys must have known already that this is OR operation and this corresponds to AND operation. Yeah. So and this so basically plus not Q and not P. So this will be just not Q times not P, right? So again, I can since this OR operation is associative and commutative, I can just remove these parentheses. I already know the properties. So I can just write this expression as, so basically, you guys understand what is the meaning of these parentheses here, right? Why are these parentheses here? Basically, this means that essentially means that you first have to calculate this part and you have to calculate this part and then you take its OR. So these parentheses denote the ordering in which you have to do the operations. But as we have seen in the lectures already, that for this OR operation, suppose there are these OR operations, here the use of parentheses is not really necessary since OR operation is associative as well as commutative. So you might as well remove the parentheses and it won't make any difference in our results. But in some other operation which is not associative and commutative, this removal of parentheses will definitely make a difference. So be careful whether the operation you're using is associative, commutative, or is it not. So yeah, basically associativity and commutativity guarantees us that the ordering in which we do the operations won't matter. But otherwise, like in matrix multiplication only, you can see that you already know that like A, B, and BA, since matrix multiplication is not commutative, A, B, and BA are different things. So yeah, just putting that information out there, so everyone can appreciate the importance of associativity and commutativity of an operator. So yeah, so this will just resolve to not P, no Q plus PQ plus, like basically this not Q times not P can already be written as not P times not Q because uh, AND operation is also associative or commutative. So this we were able to remove these parentheses just because of that associativity property. And then we can just reorder these two expressions. Fine. While I reorder, I'm just seeing that there's a not P not Q term here and there's a not P not Q term here. So I can just maybe club them together and they'll just not P times. I'll just do it step by step first. Not P times not Q plus PQ. And now this can be resolved to basically this not P times not Q plus not P times not Q is just like A, or A is basically A itself. So this will be just not P or not Q. This will just be not P or not Q plus PQ. So this expression, the expression which was given in the question, this just resolves to not P or not Q plus PQ. And we saw this sort of expression in the start also, this sort of expression, not P or not Q plus PQ. And what did this correspond to? This was basically, you can see, uh, not P XOR Q. So like just you guys can just see like not P or not P XOR Q will just correspond to this expression only, as we had done already, that like not P times not Q plus not of P, which would be P itself, times Q, as we have seen the definition of XOR operation. So this will be And the like all of this expression will basically correspond to not of P XOR Q. And the option not of P XOR Q corresponds to basically the option C. So yeah, one more thing, basically not of P XOR Q can also be written as in XOR. You might have observed this already. Since like P and Q are symmetric here, even if I replace the P and Q, like P by Q and Q by P, this expression remains same. So this is also equivalent to like not of Q XOR P. Right? So suppose in the options, this option was not there. Let's say the option C is, we know that option C is correct, like not of P XOR Q. Uh, but suppose this option was not there and instead the option was not of Q XOR P, then that option would also have been correct. Since like this expression is symmetric, like PQ plus P bar Q bar. So it can be written either as not P XOR Q or not Q XOR P. Both of these representations are correct. So yeah. So in this way we can see that option C was correct here. Again, alternate method would be truth table, but again reiterating that is not something which we are going to do right now. So yeah. So the seventh question, maybe I'll just put this in this page. So the seventh question says that, one second, guys. Yeah. So seventh question says that if the truth value of S is true, where S is basically this statement, not of not Q and not P implies P, then what are the truth values of P and Q? So basically the question is saying that the statement S is this. Maybe I'll just represent it in my notation so it's easier to understand what this statement is means. So not of, not Q times P, not Q times P, and then this whole implies P, and the not of all of this. This is what the expression S is basically saying. Like as you can see, like this not Q and this is not P. Okay. Yeah. So the expression is basically saying that not Q times not P. This should imply P, and then the negation of this whole statement, the negation of all of this. So it's saying if this is true, if like this state, the truth value of this statement is true, then what are the truth values? Then truth values of P and Q are. So again, the easiest method for this would be like, straightforward method would be check for all possible values of P and Q. Values of P and Q. Like suppose the combinations would be like both P and Q are true, or like P is true and Q is false, or like P is false and Q is true. Similarly, P is false and Q is false. So for all here, we have to just check for four values since there are four variables. It's really on the same. If PQ corresponds to these, we can check for all these pairs. In which of these pairs the value of this compound statement, this S is coming out to be true, and wherever S comes out to be true, that are the possible values. Wherever S is true, it will be a possible value for the pair P comma Q. Right, guys, this is a very straightforward way, like similar to the truth table values method, where we list out all the possible values of the Boolean variables and check. So here also we are just drawing the truth table for uh, basically this expression S, and we are seeing when does the value true hold. So maybe like just skipping this part again, like how to do it using truth table. Maybe we can try to do it by simplifying the expression and directly seeing when will these P and Q be true. So I'll just start out with this expression and try to simplify it. So maybe I would be able to see directly what are the possible values of P or Q. So maybe I'll just start by simplifying this part first. So this will just be like negation of like this whole expression E implies P will just mean that negation of this first expression plus P. As we know, like A implies B means not A or B. So this will just mean that I'll just be doing like negation of negation A times negation B and plus P. I hope this makes sense, guys. Like this negation, the outside negation, I have not touched it. It's just straightforward as it was here. And the inside expression, this whole expression, I've resolved this implication operator to not A or B form, right? And this was, sorry, this was Q and this was P. Yeah. So further trying to resolve this again. How can we resolve this? So I'll just try to now resolve this not expressions, a bunch of these not expressions. So not of not q times not p. This will just be using De Morgan's law, negation of this negation of q plus negation of p. So negation of q will give us q. Yeah, let's check it out. So the outside negation I am not touching again. I'm touching this in the inside negation part. So negation of this expression would just be like going term by term using De Morgan's law. It will just be, I'll just first go with negation of q, it would be q itself. And then there's an and operation here, like not q times not p. So that and will instead turn to or. And then this not p will, the negation of this not p will again turn out to be p. So this will be q plus p. And then this plus p was as it, p plus p was as it is. So again, resolving this, p plus p can just be written as uh, not of q plus p, because p plus p is equivalent to just p only, and this not of q plus p is just like again applying the Morgan law. So not q, the negation of q is not q, and then negation of or is and. So not q times not p. So this will just be not q times not p. So yeah, simplifying this expression, this seems like a very complex expression, but turns out this is a very nice expression, just not q times not p. So if this is true, so basically the question is saying that this is true, then we need to find the values of p and q, right? So this means not q times not p is true. Is true. So this implies basically there's an AND operator here. So AND operation is only true when both of these terms individually are true, right? So this means that not Q is true and not P is true. And this is just equivalent to saying, maybe it's not this, instead I'll use this. This is just equivalent to saying that Q is false and P is false. So basically, this and is important. So basically, when P and Q both are false, only then the statement of this, the value of this expression evaluates to true. So basically, this is the only okay, sorry. So the false is the only value which we'll see. You guys can check this using the truth table also. When you draw the truth table, you will be able to see that only at false does this expression evaluate to true? So instead of using the truth table, we have just done a bunch of simplification steps and arrived at the answer directly. That's why I was saying that uh, this is a better way to approach the Boolean algebra problem uh, using like the properties of the operators and stuff. So yeah, so Q is false and P is false is the answer. So answer is the pair PQ should be PQ is false comma false. No other value can satisfy will evaluate this to true. This was the answer. I've just underlined the answer. Yeah. Going to the next question now, guys. So any questions till now? So another like logical equivalence question. So again, just going through the same steps again, we'll be able to arrive at the solution. Maybe I'll just do it once more. So just typing this expression out in my notation. So not of P plus Q plus this or not of P times not of Q. This is our expression and we need to find its logical equivalent. So just let's just try to do it again. So this not of P plus Q will evaluate to like again using De Morgan's law. This will evaluate to not of P times not of Q. So this will just be not of P times not of Q. And then there is a plus, and here it is not of P times not of Q. So as we have seen that, as we already know that the AND operation is commutative, so this can just be written as, never mind. So yeah, so basically, as you've seen that like these both expressions are same, right? A plus like some expression A plus the same expression A. It will, the OR operation will return that expression A itself. So this will be equivalent to not of P and times not of Q only. A pretty straightforward answer. So not of P and not of Q. So that is option A. So option A. I just underline. Okay, I think I have put two expressions of the same value, like this option A and option D both have not of P and not of Q. Let's just assume one of that was. Let's copy this off. Let's just say option D was this. So yeah, it's option A is not of P time not of Q. So option A is the correct answer. Yeah. Now coming to ninth question. As you can see, like basically the simplification steps are not something which are very extraordinary. They are just straightforward applications of the properties and not too difficult to see. Okay, so Dr. Ganesh Koride is writing something. Okay, you're typing out for seventh question. You're saying that S is true, then removing negation inside the expression becomes false. That is hypothesis true and the conclusion false. That is P false. Oh yeah. The method by which you're also trying to solve this is also correct. Like you can just see. So Dr. Ganesh is typing in the chat something along the lines of trying out like if S is true, what will be the values of these variables? He's trying to find out directly. So he's just saying that suppose if S is true, so this statement S is true. So basically negation of this statement. So removing this negation operator, all of this expression should be false. So all of this expression should be false and This will be false uh, when this part is this not Q and not P part should be true, and this P part should be false. So from this we get P is false, and from this part we'll get Q is also false. So yeah, definitely that way also works. I was just trying to capture the most general method by which we approach these problems, which is generally to like simplify the problem and then just see the truth values directly. So yeah, Dr. Ganesh Korede's method is also correct, and this is how we can approach this problem also. So yeah, coming to ninth question now. So what can we infer from the below statement? So statement Q says Gautam will go for a long drive to Mahabaleshwar or he will play cards. And statement R says Gautam did not go to Mahabaleshwar. So what can we infer from these two statements? So again, like as we did, let's just scroll up. For question one, basically we broke this complex statement, compound statement into two simpler statements and then just found out the negation. Similar sort of thing will happen here also, but I'm not going to repeat that same sort of method again. We can just try to see the answer directly here. So let's just see. So if these two statements are true, like Gautam did not go to Mahabaleshwar and Gautam will go for a long drive to Mahabaleshwar or he will play cards. So, uh, so at least one of these statements will have to be true. That either Gautam will go for a long drive to Mahabaleshwar or he will play cards. One of these has to be true. And we're also given that Gautam did not go to Mahabaleshwar. So this statement, Gautam will go for a long drive to Mahabaleshwar, turns out to be false. Since at least one of these two statements should have been true, so we can say that Gautam will play cards, right? So you can just see this simply by like taking a statement A as like uh, yeah, Gautam will go to Mahabaleshwar. Statement B as he will play cards. And what we are given is like uh, Q is uh, A or B. And we are given R is not of A. And so we need to find if these both of these statements are true, Q and R are true, then what statements will hold. So we can just like using this sort of analysis also, like as we did in the first question, we can try to solve this using like proper logical expressions, or we can just see this directly also that either Gautam will go for a long drive or he'll play cards or both. Since he did not go to Mahabaleshwar, he will have to play cards. Otherwise, both statements cannot hold simultaneously. So from this, using just this method or just saying directly, both are the same things actually. So we will arrive at option B, that Gotham will play cards. So yeah, you guys can take this out later if you guys want to do it yourselves. That you can write Q statement as A or B and R is not A. So both of these should be true. So since not of A is true, so A is false. So since A is false and Q was true, so B has to be true. So he will play cards would be good name. So yeah, straightforward. I will say this also. Let's come to question 10 now. So question 10 just says if, again a straightforward question, if not of P implies not of Q is false, then what is the truth value of P and Q? So maybe we can just see the value directly if we want, or we can just try to simplify this expression. I always like simplifying the expressions, and I prefer that because by simplifying the expression, you can exactly see what is going on. Like you can always make an expression very confusing and twisted in many ways. But after simplifying, you can just see like what was the basic argument behind the expression. So I always prefer simplifying the expression first and then finding out the truth values. You can also directly try to find out truth values from here. Let's see that this statement is false, like not P implies not Q is false. So we can basically say that implication operator only returns false in the case when the first part is true and the second part is false. So it will imply that not P should be true and not Q should be false. So not P is true implies P is false, and not Q is false implies Q is true. So the answer would be like, I'll type this out properly also. And after, like, if we just want to do this only, we can just see that the answer would be P should be true, P should be false, and Q should be true. So option C. We back to this orally. But I always, as I said, I prefer it to write down the steps and do it after simplification. So let's just try to do this again in my notation as I discussed it with you guys. So this is not P implies not Q. So this can be simplified to like removing this implication operator is just equal to saying like not of P plus Q. So this will be not of P plus Q plus not of Q. Basically this expression will come as it is. So this will be not of Q. So this will be equivalent to saying like not of P reduces to P plus not Q. So yeah. So basically now we are able to see more specifically like what this expression actually simplifies to. So at least for me, it reduces the amount of thinking which I need to do after this step, like what step do we need to take. So P or not Q, then what is so this statement is false. P plus not Q is false, right guys? So the OR operation returns false only when both of these should be false. Like this implies, since this statement is true, so this will mean that P is false and like this statement like P or not Q is false, right? So this will only be true. This will only be false when both of these individual expressions are false. That is the property of the OR operator, right? So P is false and not Q is false, which is basically just saying that P is false and Q is true. So P is false and Q is true, which was option C, which we arrived at by directly looking at the property of implication operator also orally. But as I said, like this not P implies not Q can just be simplified to this P or not Q expression, and seeing things in this expression is much more easier. And it just tells you the whole story about the expression, like what this expression basically means, this complicated expressions actually mean. So yeah, in this way we arrive at this option C. So Ghanshyam, you're writing it may also be option A. So option A is true. So as we have seen that this is the only case P is false and Q is true is the only case where this expression can be false. And you can verify it also. If you put true, both of these values here, then not P will give us false. So whenever the first expression in implication operator is false, the whole statement becomes true itself. Like if you must have seen the implication Boolean operator. So basically, if not P will become false, and as soon as this becomes false, the value of this side becomes irrelevant. The whole expression will be true anyways. That's why true is not possible. Maybe you can review your mistake later that why was this, why were you arriving at true? This will be incorrect. So yeah. So after question 10. Let's cover question 11 now. So question 11 basically says state true or false. The two following compound propositions are logically equivalent. So these are the two compound statements. So we just have to see whether they are logically equivalent or not. So Huh. So how will we do this again? Like we have some hammers along with us, like the one method. One method is just check using truth tables of both expressions. So both expressions 1 and 2. So just make the truth tables for both of these expressions. So here note that each of these expressions has four variables A, B, C, D. So the truth table would contain 16 values. So one of these would contain 16 values. Similarly, this will contain 16. So overall, you'll have to check for 32 entries. So yeah, quite cumbersome work. But so one way is just check truth tables of both expressions and arrive at the answer. And another way, like as we have already discussed so many times, like maybe we can try to simplify these expressions and find out what they actually mean. So I'll just try what I'll be trying is just simplifying. Like basically both of these expressions are in a bit of complex form. We can see like both of these have like these implication signs here. So I'll just try to reduce these to like basic ands and ors. So we'll reduce both of these expressions, and after reducing both of these expressions, uh, checking their similarity becomes very easy, as you will see. So basically, let's just try to reduce both the expressions. So again, writing it out in the notation which I discussed with you guys. So this will just be not a, okay, yeah. I'll just first reduce this expression, not a plus b. I'll just first remove these implication signs. In the first expression, remove these implication signs instead of their actual meaning. So this will be not a plus b and not c plus d. And there's an implication sign in between. So this will again simplify to again removing this implication sign. They become a not of this expression plus this expression, right? So it will correspond to not of not a plus b, and then a plus and this expression as it is, not c plus d, right? So again, since these are all so okay, so one of these knots we have not resolved yet. So now resolving this knot using De Morgan's law, like not of not a not b, not a or b. So taking this knot inside, this will become not of a, which will come to a. This plus will become multiplication, and this b will become not b. I hope you guys are following me now. I have done this step several times in many questions, so I'll just write it out directly here. So this will become a times not b plus the expression which was given to us, like not c plus d, right, guys? So basically, this is the expression which it reduces to, which is basically I'm just saying, since all of these are additions, these are like associative operator, this addition operator or operator, I can just write it as, since ordering is irrelevant, a not b plus not c plus d. I hope it is clear to everyone. I have not done anything fancy here. So yeah, so this resolves to just this expression. Maybe that is it. Maybe I'll just bold it so you guys can see which expression I'm talking about. So yeah, so this the first simplifies to this expression, and similarly we can simplify the second part also. But for second part we can just apply a direct trick, as we can see, like the only difference between like first and second part is here it's just saying a implies b implies c implies g, and here this a and this a are similar, but these b and c's are interchanged, right? And everything else remains the same. So the in second part, maybe we can just switch values of b with c. Like where b was coming, we just put c instead, and instead of c, we put b, and we get the simplification for the second expression also. So the first expression was this. So maybe I'll just first take the b and instead write C, replace B by C, and then I took the C and I replaced it with B because this was the only thing which was happening. Like B was replaced with C and C was replaced with B. So in the simplified form also this will hold. So these are the, like, I think it's fairly straightforward what I did here. So from this we can see for are these statements logically equivalent or not. So these expressions are like quite different. Suppose, so basically now the question basically uh, question reduces to whether A not B, comma, these two expressions are logically equivalent, right? So these two expressions, this one, and maybe I'll just separate these like this. Yeah. So these two expressions are logically equivalent or not. So the question is to this only. So like from this, actually you can directly see for what values they might differ. So let's just see, since these are all addition operators, maybe if I take D as true, then both of these expressions will anyways be true, since these are all like additions, or like additions mainly mean OR. So if D was true, then all of these would be true in itself. So if D was true, then and then for all values of ABC, these would be equivalent. So maybe let's just take the D as false. So maybe I'm just trying to construct an example where these might differ. So in that example, we can be sure that D is false, as I said. Okay, D is false. Otherwise, when D was true, both of these expressions were true. And another thing we can say is, suppose D was false, then these both parts are removed. Now we only have to look at A C bar plus B bar and A B bar plus C bar. These two parts. So in these two parts, mm, how we can check is, so reduces to, I'll just write it down again first. I'm just trying to write it down. If they are not equivalent, then D must be false. So reduces to, so maybe if D is false, then this D won't affect these plus operation. So these two expressions are reduces to whether these two expressions are equivalent or not. Right, I guess it's easy to follow, not too difficult. Yeah. So basically these two expressions I have to check, like A B bar plus C bar and A C bar plus B bar are equivalent or not. So for this, how can I directly say uh, whether they are equivalent or they are not equivalent? So maybe let's just take the value of A. So suppose value of A was, let's say value of A was false. So both of these A B bar and A C bar both would be 0, right? And at that point, the value only depends on value of C bar, and here it depends on B bar. So are you guys following? So suppose A was, I'm just trying to construct a counter example. So let's say A is false. So in that case, like the value of first expression will depend on not C and basically on C, and the value of second expression will depend on B. So I can make C and B differ. So these two expressions will also differ. So I can just say B is true. Let's say B is true and C is false. Uh, So in that case, what would happen is this first expression would come out to be A is false, so this part would come out to be 0. So C is false, so this part would come out to be true. So first expression comes out to be true. Here what will happen is 1 is true. But in 2, what will happen is, so as A is false, this expression will be 0 and B is true. So not B would be false. So this false or false will give us false. So second is false. So for this values of ABC, like A is false, B is true, C is false, and D was false also, which we had assumed here. So their value differ at A, B, C, D is equals to false, true, false, false. Basically false to false I got from here and I assumed D was false. So at these values, 1 comes out to be true and 2 comes out to be false. So hence they are not equivalent. Right, guys? So this is how we check the logical equivalence of the expressions. So yeah. So here one thing to note here is that like one method which I just said was check using truth tables for both the expression. So in truth table also, since we are getting logically not equivalent, so in truth table also there must exist a row at which these both expressions should have differed in their truth values, right? And finding that row at which these values differ by just truth table would take longer time. But here we have just found the that row directly. Like after simplification, seeing what row is at what row are they differing is an easier task. So we have just seen that at this row, the row false, true, false, false, these would be differing. So in that sense, we are essentially doing the same thing as a truth table, but we are just doing that checking faster uh, as by simplifying the expressions. So that's why I generally prefer to simplify the expressions first and then see what is happening. So yeah. So the truth, the value, so value differ at this false to false false, hence they are not equivalent. So so note that one more thing to notice that like for saying that two propositions are logically equivalent, all rows of the truth table should match with each other. But for saying that they are not equivalent, we just need to show one row at which the values are not equivalent. Like for equivalence we need to check like us we need to find a strong condition that all the rows must be equal to each other, and for saying that they are not equivalent we just have to find one of the rows which is not equal, and then we are done. So at just one row, even if at one row we are able to find the different truth values, then we can say that they are not logically equivalent. But if we have to show that something is logically equivalent, then we have to like take the negation of it, basically say that all the rows must be equal to each other. So yeah, so this is how we got to the question 12. So question 12th is basically like maybe you guys can take it up as a practice question for yourself. Like you guys must know what are POS forms. So I'll just say that try it yourself. It's more of a like this question was more since we are running low on time. So this question was more aimed at just reminding you guys about what is POS and SOP forms. This is taught in high school as far as I remember. Also the product of sums form and SOP is sum of products form. So you guys can check this if it was discussed in the lectures also. So it's not like really difficult to know like in product of some form, we just check which rows are true and just find it. Basically from the truth table, we are able to find the, so basically product of sum and sum of product forms basically corresponds to finding a Boolean expression which corresponds to this truth table, right? So basically denote a compound proposition write a compound proposition CPQR whose truth table is the same. Generally, till now, what we were doing was we were given a proposition and we were making truth tables for it. So now suppose we are given a truth table and we want to make a proposition whose truth table would be this. So for that, we use product of sums form or sum of products form. It's not really difficult to see. So yeah. Okay, I think maybe we can try to discuss at least the product of forms, product of some forms. I can try to discuss. So product of some forms or okay. So let's just see what are the product of some forms. Yeah. Or maybe no, let's sorry for that. Maybe let's just leave this out. You guys can try it out yourself. It's just a very mechanical procedure and uh, you can easily see how it is done. Basically, the sum of from a product sum form basically corresponds to finding a proposition which follows this truth table. So nothing more, nothing too fancy. Like it's as easy as making a truth table for an expression. So yeah, let's just leave this. So we come to the future question. So I guess this is a very straightforward question. So consider an expression P implies Q implies not a. How many rows appear in the truth table for this expression? So in truth table as there are three Boolean variables. So each variable takes like either true or false. So this implies 2 to the power 3 entries in the truth table. So 2 to the power 3 is just 8. This was a straightforward question. So yeah, I hope this is clear. So yeah, 13 question like it just corresponds to like 8 entries in the truth table. Just reminding you guys about n variables, so 2 to the power n entries in the truth table. Nothing too fancy. So let's come to the fourth question. It's a bit interesting. Like not that interesting, it's more straightforward question. But yeah, still free to this. So an island is inhabited by only by knights and knaves. So knights are people which always tell the truth, and knaves are the people which always lie. So and then let's suppose we meet two inhabitants of that island, A and B. A says that B is a knave, and B says neither A nor I are knaves. So who is a knight? So basically, we are given two people A and B, and we don't know who is a knight, who is a knave, or if both are knights or both are knaves. And we need to find like and they both tell us some statements, and from these statements can we know whether they are knights or knaves. Knaves are people who always lie, knights are people who always tell the truth. So in this in these sort of in these sort of problems, you guys must have seen these sort of problems in like mental ability tests or something. So a straightforward approach for these are like using logic only. Like here like suppose we take a statement P which says that A is a knight. And similarly, like this is a statement P, which might this is a proposition P, which might be true or false. We don't know. So we need to find its truth value actually. And Q is B is a knight. Let's just say that these are the uh, two statements. And then basically what A is saying is that A says A is basically saying that B is a knave. So A is basically saying not Q. And B says that neither A nor I are knaves. So basically not Q. So A is not, so B is basically saying that A is not a knave as well as B is not a knave, right? So it's basically saying not P and not Q. Or I. Okay, sorry. I screwed up. So basically it's saying that neither A nor I are knave. So B is basically saying that neither A nor B are knaves. So B is basically saying that A and B both are knights actually. So he's saying that actually A and B both are knights. So B is basically saying that A and B both are knights. Basically, we see that neither A nor I are knaves. So if they both are not knaves, then they both are knights. So B is basically saying that B is a knight, A is a knight, and Q is a knight. B is a knight. And similarly, A was earlier saying that B is a knave. So basically, negation of this, B is a negation of B is a knight is B is a knave, right? So also we don't know the truth values of these two statements, right? Maybe suppose A was a knave. So this statement might in itself be false. So we don't actually know whether these statements are like what A is saying is true or whether A is saying something false. So here, how can we approach this question is basically here we can take like all the possible values of P and Q. Like suppose P and Q was, and we try to check like we take all the four possible values like P was true, Q was true, P was false, Q was true, and like all the possible four combinations of P and Q, and see whether all of these statements are consistent with themselves. So this is how we try to basically we try to make a solution, which is we try to see if suppose P and Q both were knights, whether all these conditions can be upheld simultaneously or not. If they are not able to be upheld simultaneously, then that means that P and Q both can't be knights and stuff like that. So let's just see how we do this. So let's just assume first we'll take the four cases. So we can take the four cases for P and Q. So cases on P comma Q. Basically, what I mean by cases is that I'll first assume that A is a knight and B is a knave, like A and B both are knights, let's suppose. And then I'll try to find out whether both of these conditions can be upheld simultaneously or not. Stuff like that. So case one. Case one is true, true. So both of these P and Q, both statements are true. So basically A is a knight as well as B is a knight. Let's just assume in this case, maybe I'll just first write down all the cases so that we don't have to come back to that again. Case two is case three, case four. False, false. Case two. These are the four cases which might be happening. So we need to find which of these four cases can actually occur. Right. So case one is true, true. So in that case, if case one in case one, basically it says that A and B both tell truths. So if A and B both are telling truths, then this implies not Q is true, not Q is true, and also like not Q should be true. Also, the statement which B says, B is saying P and Q is true. These both statements should be true, right? Because A and B both are telling the truth. So A was saying not Q and B was saying P and Q. So both of these statements should be true. Just these are the two statements. Not Q is true and P and Q is true. So if both of these statements are true, then for this statement, the not Q for this to happen, that not Q is true, this implies that Q is false, right? Not Q can only be true when Q is false. But we assume that in this case that Q was true, right? Are you guys able to see what I'm saying? I'm basically saying that suppose the case was that P and Q both statements are true. In that setting, basically A and B both are telling the truth. So A is saying not Q. So basically not Q is true. Since not Q is true, Q should be false. But in this case, we assume Q to be true. So we arrive at a contradiction here. So this case is not possible. So contradiction, hence not possible. Yeah. So this case one is not possible. Both can't be, both P and Q can't be true. So let's say case two is there, like Case 2 is P is true and Q is false. Basically, A is a knight and P is not a knight. So A tells truth, P tells lies. So this implies that not Q is true, since A was telling the truth. So not Q is true. So this will imply that Q is false. This is from just A. Like A says that not Q is true and A was telling the truth. So from this we obtain that Q should be false. Right. And like still now we are consistent since we assume Q to be false. So now coming to the statement of B. So B is saying P and Q. Right. In this case, P, what is P and Q? Like P and Q is basically P was true and Q was false. Right. So P and Q evaluates to false. So what B is saying is false. P and Q is false. One. Uh, so first part we can say that. So A tells the truth here. Since Q was basically what A was telling was not Q is true and Q is false. So A was telling the truth here. So no contradiction. Similarly, P and Q is false. In this case, P and Q basically is false since P is true and Q is false. And so what B was saying was uh, basically a lie. B was saying that both are knights, and this is not the case. So B tells lie. B tells a lie. So B is telling a lie basically because the statement which B said evaluates to false. So and since B was a and since in this case we assume like B is not a knight, B is a knave. So this is also consistent. So B should be telling a lie since he is a knave. So consistent solution here. So consistent solution. So this is a possible solution. So one of the possible values. So one of the possible values is this that uh, A is like A is a knight and B is a knave. Like P is true and Q is false. Because in this case, what we see is that the what A is saying evaluates to true. Since A was a knight, he should be saying a truth. And what B is saying evaluates to false. Since B was a knave, it should evaluate to false. So in this sense, we get this answer is correct. So suppose in case 3, what we get. So this is a possible solution, case 2, and I hope it's clear to you guys. So similarly, in case 3, what we get is like case 3 is P is false and Q is true. Basically, A is a knight and A is a knave and B is a knight. So basically, A tells lies and B tells truth. So this will imply that in this case, basically, not Q evaluates to basically A was saying not Q, and not Q. Basically, A was saying not Q and not Q evaluates to false here. Not Q evaluates to false here. So what A was telling was a lie. So A tells lie here, which should be possible, which should be true because like A was a knave in this case, so he should be telling a lie. And similarly, what B says here is that B says uh, what B was saying was P and Q, right? Maybe I'll just so P and Q here is so P was false and Q was true. So P and Q evaluates true since like P was false and Q was true. So P and Q, P was saying P and Q, so P and Q evaluates to false. So what B is saying is actually lie here. So B tells a lie here. But in this case, we assume B to be a knight, so he cannot lie. So this is a contradiction, as B cannot lie as he is a knight, right? Hence not possible. This case is not possible. And similarly, when both are false, this means A and B. In this case, A and B both should be lying, right? So what A was saying was A was saying not Q. A was saying not Q, and here not Q is basically, since Q was false, not Q is true, right? And since A is basically, since not Q is true, so what A was saying was truth actually. So A said not Q, and since Q was false, so not Q resolves to true. So A tells the truth here. So A is telling the truth here. But since we assume that in this case, like A was a knave, but A cannot tell the truth as he's a knave in this case. In case 4, we assume like P to be false. That is, A is not a knight, he's a knave. So A cannot tell the truth as he is a knave. I hope it's clear. So we arrive at a contradiction. Hence, not possible. So the only case which was possible was this case 2, which is P is true and Q is false, which basically says that the answer is that like P is true means A is a knight, and like Q is false, so basically B is a knight is false, so B is a knave. So this is the only possible answer. This answer. Okay. So yeah, so this is the only possible answer. So yeah, I hope this was clear. I rushed through it a little, but I guess since I covered all the cases, you guys would have understood what I meant to say in this question, right? Basically, what we did was we just checked what A was saying and B was saying was whether true or false in all of these cases. And on basis of that, we told whether it is possible or is it a contradiction. So yeah, so let's come to this 15th question. 15th question is a bit interesting question. So this, suppose I tell you a statement, which is this statement is false. Is this a proposition or not? It's a tricky question. So I'll just tell you guys that basically definition of proposition is like, let's just recall what is a proposition. Proposition is something which has uh, either true or false truth value. But yeah, so basically something which has either of basically a proposition is something which is either true or false. So basically something which is either true or false. This is the basic definition of a proposition. So let's just say, so basically this statement since like if this statement was a proposition, let's say, so basically this statement must either be true or false. So let's just call this statement as statement P for ease. Let's just say the statement P is this. This statement is false. This is a sentence, this statement false, and I'm just taking it to be P. So suppose if it was a proposition, then it must be if P was a proposition, if P is a proposition, then it must be either true or false, right guys? So okay, let's take cases. So suppose in case 1, P is true. Then this means that this sentence, this statement is false. P is true means that this statement is true, that this statement is false. So do you guys see that what I'm meaning to say here? This statement is false is true. So if this is true, basically if this statement is true, that this statement is false, this sentence is true. So this means that this sentence should actually be false. So this implies P is false, because since this expression is true that this statement is false, so this means that P should be false. But in this case, we assume P to be true. So in this case, what we are arguing it as that if P was true, then P was false, like, which is something which does not make sense at all. So this case is not possible, since the proposition should either be true or false. In this case, it says if proposition was true, then it was false as well. A proposition can't be both true and false at the same time. Similarly, in case 2, suppose P is false, then this sentence that this statement is false is false, right? So do you see the conundrum here? That so again, like this statement is false. So this means that P should be true actually. Like if the sentence this statement is false was actually false. So this means that this sentence was actually true, which means that P should be true. So in this case, we get that if P is false, then this implies P is true. So again, since proposition should have unique value, so this was also not possible. So in both the cases, this statement was so this statement, even if it was true, then the case this statement, this proposition is true, that case was also not possible, and false, that case was also not possible. Since a proposition must be either true or false, and both of these cases are not possible here, so P is not a proposition. So, it's a bit confusing thing and contradictory thing that like, so basically what we have proved is that like if it was a proposition, then if P is true, then P is false, and similarly if P is false, then P is true, which is something like which doesn't make sense at all. So that's why this statement is not a proposition. I hope you guys understood what I meant. This is one of a more trickier questions, and as for me, I like this question a lot because it tests the basic definitions of proposition and makes you think a little bit. So yeah, this was the last question. So with this, we are done with the logic. We are done with the logic assignment, basically the logic practice problems. So I had also planned to discuss with you guys some your doubts related to the assignment 2 solution or something. But since we are running out of time, I'll just say that you guys can post your doubts on the discussion forum, and there maybe you guys can get your doubts resolved related to assignments. So yeah, so that's it, guys. Thank you. Uh, Problem solving link, actually it will be shared with you guys, I believe, in a few days. In a few days, these the problems which I'm discussing with you, these will be shared with you guys as PDFs. So you don't need to worry, Tasi. They'll be shared with you. So yeah. So I guess that's it. Thank you for joining, guys, and I'll see you guys. Hopefully, I'll see you guys next week also. So all the best for the submissions. I think you have submissions tomorrow for the logic assignment, right? So all the best, guys, and thank you for joining. Bye bye.